Hello and welcome to the Power Analysis webinar. My name is Rupert and I'm Application Engineer for Power and E-Mobility, and I'm located in the Austrian office in Kumberg. Today I will show you some highlights of our Power Module in the software, and therefore I've prepared a small presentation and some demo files. So where do we actually need power analysis? Then we will talk about Dewesoft Power Analyzer highlights, also about voltage and current measurement. I will give you a short overview of our different current sensors and transducers, and then I will show you power analysis with Dewesoft. I've prepared a one-phase demonstration and a three-phase demonstration. So where do we need power analysis? We have the classical motor and generator testing, inverter testing, of course. Then we have on transformers and substations application, we have wind power and solar power. So also according to FGVW TG3, also included with report generation, for example. Then we have railway application, of course, electric vehicles, or at electric buses or electric planes or heavy machines, and electric equipment, and also combined, for example, with EN 5160 report. So we have from small power to very high power, more than 100 megawatts application through the whole spectrum. So let's talk about the Dewesoft Power Analyzer highlights. On the left-hand side, we have the hardware. So with 1 megasample per second, we have the high sampling rate. We have also high accuracy with 0.03% of reading, and our voltage inputs are up to 1600 volts DC. We have the safety category 2 1000 volt and 3 600 volts. On the right hand side, you see the software highlights, for example, the classical power analyzer with more than 100 calculated values like active, reactive, apparent power, power factor, cosinus phi. Then we have the oscilloscope functionality through the raw data storing. We can also show this with full sampling rate. Then we have the FFT and power quality meter, the FFT 2D, FFT harmonic, FFT 3D, FFT waterfall, FFT higher frequency, interharmonics, flicker, emission, etc. Then we can trigger also on analog, math, or power channels. So, for example, to record voltage drops or current drops. Then we have the data logger functionality and recorder functionality. So we can store the raw data in full sampling rate. And we have the post-processing functionality, which means that we can add or delete calculations afterwards. And then we can combine the existing system also with batteries to get a mobile measurement system. We can go up to 64 channels in one device, and then combine it to the next 64 channels and so on. And we can add analog, digital, counter, GPS, cam, video, also completely synchronized. So the typical measurement application on the inverter can be look like this. We're measuring before the inverter and after the inverter to do inverter efficiency measurement. So we have on the left-hand side 1 power meter, on the right-hand side also 1 power meter. Then maybe we need a CAN log, a data log, a power quality meter, GPS, and scope. And the problem here is that we have a couple of instruments. Data synchronization is nearly impossible. Data merging is also very hard. And we have, of course, no raw data. And the Dewesoft solution will give you just one device to measure all measurement points in one device, also with mechanical parts, and this also combined with GPS, CAN, decom, temperature, and video, completely synchronized. We have different instruments for this. We have the small power analyzer with just 1.5 kilograms, which is the smallest power analyzer on the market at the moment. And we have rack solutions up to 24 channels or all-in-one instruments with 64 channels or up to 64 channels. Ultimate all-in-one with battery, display, and so on. And we can connect any current transducer to our system. So, for example, at transformer testing, we can use the smallest power analyzer in the world, like the standard power analyzer with 4 times high voltage input and 4 times low voltage input, and can put it, for example, near it to the control box. For aerospace testing, if we measure on every motor or at the kitchen, the window heater or other loads, and also the AC-DC converter or the batteries, we have a lot of channels, and therefore we have the flexible hardware, which gives us high channel count. At wind power testing, for example, we can do wind power performance analysis, wind power quality analysis, low voltage transfer test, over voltage transfer test. So we have, if we do distributed measurement, we have the possibility with hardwired online synchronization between the devices. So also very flexible for this. And here we can also add this standard instruments, and then in the software also with our FGW TG3 report generation. Then if we measure on substations, we have very flexible hardware, which means also if we have distributed measurement, we can have, for example, 2 R2DBs with GPS, and between these 2 devices we have Ethernet connection or something equivalent to this, and can do a distributed offline synchronization. Or we have a test bed, then we can go also via fiber optic to the test bed and can do remote access also. Then let's talk about voltage and current measurement. We've talked about the measurement range. This is up to 1600 volt DC. We have the safety category 2 1000 volt and category 3 600 volts. We have the accuracy of 0.03% of reading. So if you take a look on the IEC 60034-21, the measurement requires there 0.2% of the whole measurement chain. So that's also, we can afford this and fulfill the requirements of the standard. And we have the high sampling rate with 1 megasample per second to measure also switching frequencies up to 100 kilohertz accurate. If we measure higher voltages, then we can use voltage dividers, active, passive isolated, or voltage transducers. The ground connection needs to be connected, but it can be directly connected to the LV input. So this will be, therefore we can also measure higher voltages. Then let's talk about current transducer. We are able to connect these different current transducers to our system directly. So we have the possibilities to add shunts, iron coil clamps, AC-DC flux gate clamps, Rogowski coils, AC-DC Hall clamps, or zero flux transducer. So depending on the application, we should use the correct current transducer. So if we want to do grid monitoring, we can use iron coil clamps, for example, or cheap Rogowski coils. We can only measure DC, but we have to also be careful about positioning, error, and so on. But we can also use a zero flux transducer for grid monitoring, for example. But if we want to do e-mobility testing or power analysis, then we should really go for the more expensive one, like the Hall compensated AC/DC clamp or flux gate or zero flux transducer, just to get also very accurate results. And most of the time it's also needed from the standard. So we've talked about the accuracy of 0.03% of reading. So what does this actually mean? The amplifier, the filter, the AD, they all have linearity, temperature drift, accuracy, noise, and bandwidth. And inside this, we have the 0.03% accuracy of our power analyzer. So the interesting part is, of course, outside of the device, the sensor itself, which also have linearity, temperature drift, and accuracy. So depending on the application, we should really go for the more expensive one if we need to get as close to the 0.0% free of reading accuracy. So in how to connect this to our system. So the iron coil, the Hall clamp, the Rakowski coils, and the shunt can be directly connected to the LV input. We have also test chip included that we can do just plug and play measurement. It will be read out, the software will read out the correct settings and the excitation for the current transducers, and we can directly start measuring. For the flux gate and the zero flux transducers, because of their high current consumption of the clamps, we need our power MCDS2 module. In Dewesoft, we have the possibility of FFT sensor correction. So what does this actually mean? So every voltage and current transducers always have a frequency-dependent amplitude error and phase shift. And in Dewesoft, it's possible to correct this error for the whole frequency range. So this means the advantage of this is that we get more accurate results. Then let's talk about power measurement. If we haven't added it yet, we can add inside the software with more our power analysis tool to do power analysis, and it will be shown like this. We can do on the top, we can add more power modules, then we can do basic configuration, single phase DC, what else? We have line frequency can be changed, the output unit can be changed, voltage source, a frequency source, which input, analog input, the frequency should be calculated, and number of samples can be changed. Nominal voltage should be about the nominal voltage we are measuring, and we can use sample rate divider inside the power module. The different wirings, and we have basic calculations and some power quality and energy calculations, with which we go more in detail with. I will show you this in the software. So let's switch over to the software. Okay, so here we are now in the software. So this is I'm now in analysis mode. So I've opened the data file, which called light bulbs. So in this case, we measured just one phase, voltage and current. Current was measured with a shunt, and to go more in detail, we have the different possibilities of power system configuration. So we can DC single phase, three phase star, R1 delta, V two phase or three phase 2 meters. We can change the line frequency from some given one for railway application or aerospace application to variable frequency, for example, for e-mobility testing. Output units can be changed, voltage source, the frequency source that can be changed, voltage, current, external arbitrary channel, number of cycles, also 10 or 12, for example, if you have 50 or 60 hertz line frequency, nominal voltage, and of course the calculation sample rate divider. Then we have basic calculations, which will be always calculated, like PQS, power factor, cosinus phi, and the distortion values also. And then we can add period values with 1, 1.5, 1, 2, or 4 with given overlap. Also added for the fundamentals. With three-phase system, we can also calculate the waveforms, the line voltages, and so on. We can add energy calculation, or negative or positive. In the power quality, we can add the harmonics calculation, so harmonics, grouping harmonics with phase angles, PQ values, impedance or interharmonics, the sidebands, the halfbands, according to the given standard can be added. Harmonic smoothing filter can be added, or full FFT. We have the distortion values here with THD, THC, and TDD. The group FFT lines for the 200 Hertz bands and the 2 kilohertz Hertz bands. For if we have a three-phase system, then we can also add the symmetrical components here and calculate the period symmetrical components if we have the period values available or activated. And rapid voltage changes can be added, and voltage flicker and flicker emission. At flicker emission, we can switch between total short circuit power or grid impedance. This should be input here, and the different phase angles. But this we don't need now. So if we talk about power, we can say, yeah, why we need our power module. We can also say, just calculate voltage times current, what I've done in our math module, and then compare these results. If we take a look, we have here now a demonstration with video also. So on the right-hand side, we have the standard light bulb, and on the left-hand side, we have the energy-saving bulb. So if we take a look now, we are measuring 46 watts. So if we compare this to the result of our math module, just add and click this here. We have principally the same result. We have the oscilloscope here, so we can add, or we can full scale this and take a look on the waveform and see, oh, nice sinusoidal wave. On the harmonic side, we see absolutely principally no harmonics. So this is an ohmic load. And yeah, but if we switch on the energy saving bulb, what will actually happen? We see a non-sinusoidal wave on the current side anymore. We see that the math power is different from the active power. So the math power will give us the apparent power. And we see also that the results are different. So, and on the harmonic graph, we see the third, the fifth, the seventh, and the ninth harmonics, the ninth order, sorry, is they are all over 20%. So we have, for example, on the ninth order, still 12 milliamps. So that's why we actually need the power module to get correct results. So just calculating U times or voltage times current is not correct anymore because of the non-ohmic load of the energy saving bulb. And we have a distortion level of more than 80%, which is really, really bad. Okay, so for the second demonstration, we have a three-phase demonstration. This was measured on an electric vehicle. Here we have also a combination of different signals. We have the power recorder here. We have measured it with GPS. We have done the inverter measurement. So we have, after the inverter, we see the typical inverter voltages, vectorscope, Now it's power consumed. Now it's recuperation with negative power now at the moment. We see the FFT chart, the switching fundamental frequency of the motor. And we have, of course, the switching frequency here, which is more or less about 16 kilohertz. The fundamental frequency is now 152 hertz. So in Dewesoft, we have the possibility just to do this also live, so we can directly see the results, the accurate power and FFT and GPS synchronization, so or with video completely synchronized measurement. So this was also an example for a three-phase measurement. This will bring us to an end. Thank you for watching, and see you next time.